In this lecture, I will talk about on a buckling of column, basically on how to solve numericals on limitations of Euler's theory and Rankine theory. First we will see limitations of Euler's theory. Euler's derived one formula which is applicable for the long column. He derived the formula on certain assumptions. The first assumption is that column should be straight and load is applied is always axial, but in actual practice we can't apply load at the axis. It may be some eccentric, or column may be a slightly bent. That is one limitations. And second, it is not applicable for the short column. We can see if crushing trace is greater than or equal than buckling straight, then only we can apply the Euler's theory. But in case of brittle material, crushing trace is less than the buckling. So at that time this theory failed. So this is the limitations of Euler theory, or simply I want to say Euler's theory is not applicable for the short column, it is applicable for only long column. To overcome this difficulty, Rankine derived one formula that is empirical formula. That formula can be used for the calculation of ultimate load both for short and long column. It gives the ultimate load that column can bear before failure. If column is short, calculated load will be known as a crushing load, and load will be buckling or critical or crippling load in case of long column. So that formula derived by some mathematical formulae, here he has used that reciprocal of Rankine load and reciprocal of Euler's load. Finally he derived the formula that is PR equal to sigma C into A, that is proportional limit, or we can say crushing trace, into area of cross section divided by 1 plus alpha. This alpha is a Rankine constant, LE by K bracket square. LE means effective length of a column, K is the slenderness ratio. This Rankine constant is equal to sigma C divided by pi square E. I will see how to solve the numerical on Euler's limitations. So this is the given problem. The steel bar of a rectangular cross section 60 by 80 mm and pin at each end is subjected to axial compression. So means both end pin jointed given. If the proportional limit of the material is 210 MPa and Young's modulus equal to 200 GPa, determine the minimum length for which Euler's equation may be used to determine the buckling load. So in this problem, cross section is given, then crushing trace, or you can say proportional limit, is given 210 MPa. For that proportional limit, we need to find out up to which length we can apply Euler's formula, and for which length this Euler formula is not suitable. So first we will write the given data according to statement. We need a cross section. Cross section is a rectangle with a breadth equal to 60 mm, depth equal to 80 mm. sigma c crushing stress, or we can say proportional limit, equal to 210 MPa. Young's modulus equal to 210 GPa, 210 into 10 raised to 3 Newton per m square. Now we'll solve this problem. So first we need to find out the minimum length for the Euler equation. So we will find out by using Euler's limitation. So Euler's limitation is that crushing stress should be equal to or greater than buckling stress. Then we can say that column will fail by buckling. So that sigma c should be greater than or equal to buckling stress. The buckling stress formula for buckling stress is pi square EI divided by LE by K square. According to statement, we need to find out effective length or actual length of column for which we can apply the Euler theory. So this formula is just interchanging term. We'll get here LE by K bracket square equal to pi square EI divided by sigma c. Where K means radius of gyration, and we know that we can find out the radius of gyration. That formula is K equal to under root I by A. I means moment of inertia. This is the least moment of inertia divided by cross sectional area. So this is the rectangle. So it will have a two moment of inertia, that is Ixx, Iyy. So to find out the Ixx, this is the standard figure. So formula is a BD cube by 12. B means breadth, D means depth. So Ixx value is 2.56 into 10 raised to 6 mm raised to 4. Now Iyy means moment of inertia about the y-axis equal to dB cube by 12. So here this is the B and D. So 18 to 16 cube divided by 12. So finally we got moment of inertia about y-axis, that is 1.44 into 10 raised to 6. Now value of K minimum, just put the value of Iyy in this equation. Area of a cross section is 16 to 80. So finally we get the value, got the value 17.32. Now to calculate the LE, put the value of E, I, sigma c and K in this equation 1. Will get the value of LE. So in this way we got the value LE equal to 17.72 mm. This is the effective length, but actual length, that we know that for both pin and jointed, effective length equal to original length of a column. That is, so according to that, L also equal to 1720.72 mm. So that was the procedure for to solve the numerical on limitations of Euler theory. Now we'll see numerical on Rankine formula. So this is the given problem. A hollow cast iron pipe having outside diameter 200 mm and thickness 20 mm and 4.5 meter long is fixed at both the ends. Calculate safe load by Rankine formula using FOS equal to 2.5 and compare Euler's load to Rankine load. Take proportional limit 550 MPa, alpha, that is Rankine constant, equal to 1 by 1600, and E, that is Young's modulus, equal to 1 into 10 raised to 5 MPa. So according to the statement, first we will write given data. The cross section is important to calculate the moment of inertia. So cross section is given hollow circular with outside diameter is given 200 mm, thickness is given 20 mm, but inside diameter is not given, but by using this thickness we can calculate the inside diameter. Sigma c, that is crushing stress or proportional limit, is given 550 MPa. That is the limit of compressive strength, E equal to 1 into 10 raised to 5 Newton per mm square, that is Young's modulus. Factor of safety is given 2.5 and Rankine constant alpha is given 1 by 1600. And according to statement, we need to find out Rankine safe load, and we need to compare this Euler's load and Rankine load. So we'll compare by taking the ratio. Now we'll go for the solution. First we'll find out the inside diameter, that we can easily find out. Inside diameter equal to outside diameter minus thickness, so 180, we'll get finally 180 mm inside diameter, because outside diameter 200 mm, thickness is 20 mm. Now cross section area of a hollow pipe equal to pi d square minus d square divided by 4. So area equal to 46.37 into 10 raised to 6 mm square. Now this is the cross section. This is symmetric about x-axis, y-axis. Now to calculate the Euler's load, we are going to use formula P equal to pi square EI divided by LE square. Let it be equation 1. To get the Euler's load, we need value of E, we need value of minimum moment of inertia, we need the value of LE. So we know the value of E, we know the value of LE. So to calculate the moment of inertia, so this is symmetric about x-axis, y-axis. So value of Ixx, Iyy will be same, and this is the standard figure. So we can use formula pi into bracket d raised to 4 minus small d raised to 4 bracket complete divided by 64. So in this way, if we put outside diameter, inside diameter in the above formula, we'll get the value of moment of inertia. Here we need not to get two moment of inertia because of symmetric about x-axis and y-axis. So this will be the minimum moment of inertia, and we know that if both ends of a column are fixed, then equivalent length equal to 0.5 of actual length. So actual length is given 4.5 meter. So we'll get the effective length for particular condition 2.25 meter. So just put the value of I, that is moment of inertia, effective length, and Young's modulus in the Euler's formula. We'll get the value of P equal to 9040 kilonewton. Now we'll go to find out the Rankine load. The formula for the Rankine load is PR equal to sigma C into A. Sigma C is the crushing stress or proportional limit, divided by 1 plus alpha, alpha is the Rankine constant, into LE effective length, divided by K, K is the radius of gyration, bracket square. So to calculate Rankine load, we need to calculate value of K. Sigma C value is given, value of A already we calculated, value of alpha is given, value of LE is also we have calculated during the calculations of Euler's load. Just we need to calculate the value of K, and we know the formula for the radius of gyration, that is K equal to under root I by A. So just put the value of moment of inertia and value of area. So in this way we will get the value of K minimum. So in this case we got K minimum equal to 64.03 mm. Now put these all values in the Rankine formula. We'll get the Rankine load, that is PR equal to 3510 kilonewton. According to statement, we need to find out the safe Rankine load. Safe Rankine load means Rankine load divided by factor of safety. So for this particular problem, factor of safety is given 2.5. So PR safe, by calculation we got the value 1404 kilonewton, that is the safe Rankine load, and final element we need to find out, that is comparison between the Rankine load and Euler's load. So here P divided by PR equal to 2.57. This is the mistake. P divided by PR means Euler's load to the Rankine load, that ratio is 2.57. So we can say Euler's load is 2.57 times greater than the Rankine load. So in this way we can solve the problem on a Rankine theory. Thank you.